SwayamPrabha. Digital India. Educated India.
Sludge management, lecture number 10. Slowly we are moving towards the intense information about textile effluent, and we have been mentioning that textile effluent treatment generates sludge. Now, how do we dispose these sludge? Because they are formed in large quantities. So, sludge management is also something that we will have to look into very carefully and understand what are the nuances of sludge management. Sludge management is an important aspect of textile effluent treatment, as it involves handling and disposing of the solid residue generated during the treatment process. Here is an overview of sludge management in textile effluent treatment. Sludge generation. Sludge is typically generated as a byproduct of physico-chemical treatment processes such as coagulation, flocculation, sedimentation and filtration. It consists of suspended solids, precipitated contaminants and biomass from biological treatment processes. So, there is a huge amount of sludge that is generated. Sludge thickening. Sludge produced in textile effluent treatment is often dilute and contains high water content. Thickening processes such as gravity settling, dissolved air flotation DAF or mechanical thickening are employed to increase the solids concentration in the sludge, reducing its volume for subsequent handling and disposal. Sludge dewatering. Dewatering process, as the name suggests, such as centrifugation, belt filter press or vacuum filtration are used to further remove water from the thickened sludge, resulting in a cake-like material with high solids content. Dewatering reduces the volume of the sludge for transport and disposal, making it more cost effective. Sludge disposal. Several options are available for disposal of textile effluent treatment sludge. Land application. Sludge may be applied to agricultural land as a soil conditioner or fertilizer, provided it meets regulatory requirements for the contaminants and pathogen. So, if it is devoid of contaminants and pathogen, then it can very well be used for soil conditioner. Incineration, that is burning. Sludge can be incinerated at high temperatures to reduce its volume and destroy organic matter, pathogens and hazardous compounds. Incineration is effective for minimizing the environmental impact of sludge disposal, but requires significant energy input. So, that means a large amount of energy is required because the incineration takes place at very high temperature. Sludge dewatering is an essential process in wastewater treatment plants to reduce the volume of sludge produced and to facilitate its disposal or reuse. There are several techniques commonly used for sludge dewatering. Now, one of them of course is centrifugation. Centrifuges are machines that spin sludge at high speeds to separate solids from liquids. The centrifugal force causes the solids to settle at the bottom of the centrifuge, allowing the water to be removed more easily. Belt filter press. This method involves passing sludge between two belts which squeeze out the water, leaving behind dewatered sludge. It's particularly effective to sludges which have high solid content. Filter press. Similar to belt filter, filter press use a series of plates with filter cloth to squeeze out water from sludge under high pressure. It is suitable for sludges with low solid content. So, belt filters are suited for high solid content and filter press are more suitable for lower solid content. Drying bed. Drying beds are shallow basin filled with sand or gravel where sludge is spread out to allow water to drain away. The remaining sludge gradually dries out through evaporation and drainage. Centrifuge thickening and dewatering. This method combines thickening and dewatering processes in a single step using a centrifuge. It is effective for sludges with high solid content. Dewatering bags or geotextile tubes. Sludge is pumped into large bags or tubes made of geotextile material. As water drains out through the fabric, the solid are retained, resulting in dewatered sludge. Thermal drying. Thermal drying involves heating the sludge to evaporate water, leaving behind dried solids. This method requires significant energy input but produces a more stable end product. Electro-dewatering. Electro-dewatering applies an electrical field to the sludge, causing the water to migrate towards the electrodes, where it can be removed. It is an emerging technology with potential for reducing energy consumption compared to thermal methods. Although thermal method is very good, very effective, but very cost effective. Decanter centrifuge. Decanter centrifuge are specialized centrifuges designed for continuous separation of solid from liquids. They are particularly useful for sludges with high viscosity. Polymer conditioning. Adding polymer chemicals to sludge can improve its dewaterability by enhancing the aggregation of solid and prompting water release. Because polymer is hydrophobic, this method is often used in conjunction with other dewatering techniques. So, each technique has its advantages and limitation, and the choice depends on factors such as characteristic of the sludge, the desired level of dewatering, available space and budget consideration. Methods of sludge disposal. Just now we studied the method of dewatering so that the sludge can be transported in a solid form. And now we will see how sludge disposal is done. Sludge disposal is a critical aspect of wastewater treatment as it involves the safe and environmentally responsible handling of the byproducts generated during the treatment process. Here are some common methods for sludge disposal. Land application. Treated sludge, also known as biosolid, can be applied to agricultural land as fertilizer and soil conditioner. Before application, the sludge undergoes further treatment and testing to ensure that it meets regulatory standards and poses no risk to human health or to the environment. That means it should not have any pathogen or any toxic chemical, otherwise it cannot be used as a soil conditioner. Land filling. Some sludges, particularly those with high levels of contaminants or that cannot be beneficially reused may be disposed of in engineered landfills. Now, what does engineered landfill mean? That a landfill with inner coating properly designed outside the city limits are constructed for such dumps. They are dumping yards. These landfills are designed to prevent leachate and gas emission, minimizing the potential for environmental contamination further on. Incineration. Sludge incineration involves burning the sludge at high temperatures to reduce its volume and destroy organic matter. Incineration can be viable option for sludges with high organic content or those containing hazardous substances. It also produces energy in the form of heat, which can be recovered and used to generate electricity. Anaerobic digestion. Anaerobic digestion is a biological process in which microorganisms break down organic matter in the absence of oxygen, producing biogas, mostly methane, and stabilize sludge. The biogas can be used as a renewable energy source, while the digested sludge can be further dewatered and used as biosolids or disposed of through other methods. Composting. Composting involves the aerobic decomposition of organic matter, including sludge, to produce a stable, nutrient-rich material that can be used as soil amendment. Sludge composting typically requires mixing the sludge with bulky agents such as wood chips or sawdust to optimize the composting process. Deep ocean disposal. In some regions, treated sludge may be disposed of in deep ocean water, following strict regulatory guidelines to minimize environmental impact. Deep ocean disposal is typically reserved for sludges that cannot be effectively managed through other methods and where land-based disposal options are limited. So, thermal drying. Sludge can be dried under thermal processes such as drying beds, rotary dryers, or thermal drying facilities. Drying reduces the volume and weight of the sludge, making it easier and less costly to transport and dispose of. The dried sludge may be incinerated, landfilled, or used as a supplemental fuel in the cement kiln or other industrial processes. The choice of the sludge disposal method depends on various factors, including the characteristic of sludge, regulatory requirements, environmental considerations, available infrastructure, and cost effectiveness. So, we cannot just dispose of sludge like that. We have to make a strategic plan as to how we will dispose this, and before doing that, the characteristic of the sludge has to be analyzed, regulatory requirements have to be kept under consideration, environmental considerations have to be kept in mind, available infrastructure, and how cost effective is the method of disposal. All this has to be kept in mind. Determining the best method of sludge disposal. Now, out of so many methods, how do we determine which is the best method for the disposal of sludge? So, determining the best method of sludge disposal depends on various factors such as characteristic of sludge, environmental regulation, available resources, and specific goals of the wastewater treatment facility. Here are a few considerations to help determine the most suitable method. So, first, characteristic of the sludge has to be found out and analyzed. Composition and characteristic of the sludge play a significant role in selecting the disposal method. For example, Sludge with high organic content might be suitable for anaerobic digestion or composting, while sludge with high concentration of heavy metals or other contaminants may require specialized treatment of disposal methods like incineration. Over and above, we have to keep in mind the environmental impact. Minimizing the environmental impact of sludge disposal is critical. Methods such as land application and composting can provide beneficial reuse of the nutrients and organic matter while minimizing reliance on landfills and reducing greenhouse gas emission. It is essential to consider factors such as air and water quality, soil health, and potential impact on the ecosystem when evaluating disposal options. Regulatory compliance. Compliance with local, state, and federal regulation governing sludge disposal is non-negotiable. Different disposal methods may have specific regulatory requirements regarding treatment, handling, transportation, and disposal practices. Ensuring compliance with these regulations is essential to avoid fines, legal issues, and negative environmental impact. So, it is not that one rule has been made and that is to be followed. Regulatory compliance would take into consideration all the factors, that what is the content of that sludge, how it can be handled, how it can be transported, and what is the best disposal practice. Resource recovery. Some disposal methods offer opportunities for resource recovery, such as energy generation from anaerobic digestion or incineration, or the production of nutrient-rich biosolids for agricultural use. These options can provide economic benefit and help offset disposal costs while promoting sustainability. Cost effectiveness. The cost of implementing and maintaining sludge disposal methods is crucial. Consideration for wastewater treatment facilities. Factors such as capital investment, operational costs, transportation expenses, and potential revenue for resource recovery should be evaluated to determine the overall cost effectiveness of each disposal option. Public perception and stakeholders engagement. Public perception and stakeholders engagement can influence the selection of sludge disposal methods. It is essential to consider community concern, stakeholders' preference, and public outreach efforts to ensure transparency, trust, and support for the chosen disposal approach. Ultimately, there is no one-size-fits-all answer to the best method of sludge disposal. Each wastewater treatment facility must assess its unique circumstances and objectives to determine the most appropriate disposal method that balances environmental, regulatory, economic, and social considerations. Often, a combination of disposal method may be employed to effectively manage different types of sludge and optimize overall resource utilization and environmental stewardship. Landfilling. Sludge may be disposed of in secure landfills designed to prevent leaching of contaminants into environment. However, landfilling is often considered the least preferred option due to potential long-term environmental risk. Anaerobic digestion. In some cases, sludge may undergo anaerobic digestion to produce biogas, mainly methane, for energy recovery, while stabilizing the organic matter content. The digested sludge, known as biosolids, can be used as soil amendment or fertilizer. Regulatory compliance. Sludge management in textile effluent treatment must comply with the local regulation and guidelines governing the handling, transportation and disposal of the solid waste and wastewater treatment residues. This includes monitoring sludge quality for contaminants such as heavy metals, pathogens and organic pollutants to ensure safe and environmentally responsible disposal practices. Landfilling of sludge is a commonly used method for the disposal of wastewater treatment byproduct, particularly when other options such as beneficial reuse or incineration are not feasible or cost effective. Here are some key points to consider regarding landfilling of sludge. Pre-treatment. Before landfilling, sludge typically undergoes pre-treatment to reduce its volume and minimize the potential environmental impact. Pre-treatment processes may include dewatering to remove excess water, stabilization to reduce odor and pathogens, and conditioning to improve handling characteristics. Regulatory compliance is applicable everywhere because sludge cannot be just dumped anywhere. Landfilling of sludge is subject to stringent regulation to protect human health and environment. Regulatory requirements vary by jurisdiction but typically include standards for landfill design, liner system, leachate collection and treatment, and monitoring of groundwater and surface water quality. So, a very concerted program is made for regulatory compliance of the landfill and sludge. Landfill design. Modern landfill design incorporate multiple layers of liners, leachate collection system and cover material to prevent contamination of soil and water resources. Engineered landfills are designed to minimize the potential for leachate generation and gas emissions and to facilitate long-term stability and environmental protection. Leachate management. Leachate, the liquid that drains from the landfill waste, can contain dissolved contaminant and must be managed appropriately to prevent pollution of groundwater and surface water. Landfills with sludge typically include leachate collection system to capture and treat the leachate before it is discharged. Gas management. Landfill gas, primarily composed of methane and carbon dioxide, is produced as organic matter in the sludge decomposes anaerobically. To prevent the buildup of gas and mitigate odor and greenhouse gas emissions, landfills may include gas collection and control system to capture and manage their landfill gas. So, it is a whole different type of chemistry and mechanical systems are required for dewatering the sludge, because there would be leachates, whether it is having pathogens and heavy metals and pollutants which are not supposed to be present for agricultural soil fertilizers, etc. All this has to be studied very carefully. The chemistry of the content of the sludge before disposal has to be analyzed very carefully. Long-term monitoring and maintenance. Landfills require ongoing monitoring and maintenance to ensure compliance with regulatory requirements and protect environmental quality. Monitoring activities may include groundwater and surface water sampling, gas monitoring, and periodic inspection of landfill infrastructure. Public perception and community engagement. Landfilling of sludge can be contagious issue due to concerns about potential environmental impact and odor. So, engaging with local communities, stakeholders and regulatory agencies to address concerns, provide information and ensure transparency can help build trust and support for landfilling activities, because people around these landfills are seriously concerned about the impact it may have in long term. So, they have to be proven that these are not so hazardous that it will create any problem in the groundwater or surface water. While landfilling of sludge can be a viable disposal option in certain circumstances, it is generally considered less preferable than methods that prioritize beneficial reuse or resource recovery, such as land application, composting or anaerobic digestion. Minimizing the volume of sludge requiring landfill disposal through source reduction, recycling and treatment option is also important for sustainable waste management practices. Sludge generation is going to happen in textile effluent treatment. So, sludge generation in textile effluent treatment occurs as a result of various treatment processes employed to remove contaminants from the wastewater. Here are some of the key points regarding sludge generation in textile effluent. So, physico-chemical treatment, coagulation and flocculation. Chemical coagulants like alum ferric chloride are added to the effluent to destabilize suspended solids and organic matter. Flocculants are then added to promote the aggregation of particles, forming a sludge that can be removed by sedimentation and filtration. Precipitation. Chemical precipitation processes may be used to remove dissolved metals and inorganic pollutants from the effluent, resulting in the formation of precipitates that contribute to sludge generation. Biological treatment. Activated sludge process. Microorganisms metabolize organic matter present in the effluent under aerobic conditions, leading to the formation of microbial biomass, that is activated sludge, that contributes to sludge generation. Anaerobic digestion. In anaerobic treatment process, organic matter is degraded by anaerobic microorganism, resulting in the production of biogas, which is mainly methane, and residual sludge. So, solid liquid separation becomes very important, because sludge has to be made such that it can be transported. Filtration. Solid liquid separation processes such as sand filtration or multimedia filtration may be employed to remove suspended solids from the effluent, resulting in the accumulation of sludge on filter media. Centrifugation. Centrifugal force is used to separate solids from the liquid phase in sludge thickening or dewatering processes, resulting in the formation of sludge cake. Chemical oxidation. Advanced oxidation processes, AOPs, such as ozone treatment or UV hydrogen peroxide oxidation, generate highly reactive species that oxidize and degrade organic pollutants in the effluent, leading to the formation of oxidized byproduct and residual sludge. So, in all these processes, sludge are generated. It is not that sludge is generated only at the last stage. Sludge characteristic. Therefore, it is important to understand the characteristics or the composition of the sludge. The characteristic of sludge generated in textile effluent treatment vary depending on the treatment processes employed, the composition of the effluent and the nature of the contaminants present. Sludge may contain suspended solids, organic matter, microbial biomass, precipitated contaminants and other constituents removed from the effluent during treatment. Sludge handling and disposal. Sludge generated in textile effluent treatment must be properly handled, transported and disposed of in accordance with local regulation and environmental guidelines. They cannot be just disposed anywhere and everywhere. Depending on its characteristic, sludge may be treated further, thickened, dewatered, stabilized before disposal through methods such as land application, incineration or land filling. Sludge thickening. Sludge thickening is a crucial step in the wastewater treatment process to reduce the volume of sludge produced and facilitate subsequent handling, dewatering and disposal. Several techniques are commonly employed for sludge thickening in textile effluent treatment. Gravity thickening. In gravity thickening, sludge is allowed to settle under the influence of gravity in a large settling tank or clarifier. As sludge settles, solid accumulate at the bottom of the tank, forming a sludge blanket, while clarified water rises to the surface and is discharged. Sludge thickening efficiency depends on factors such as sludge concentration, settling characteristic and hydraulic loading rates. Dissolved air flotation method for sludge thickening. DAF involves the introduction of fine air bubbles into the sludge mixture to float suspended solids to the surface for removal. The buoyant sludge forms a thickened layer at the surface of the flotation tank, which can be skimmed off by using mechanical scrapers or skimmers. DAF is particularly effective for thickening biological sludges with low settling rates or colloidal solids that are difficult to settle by gravity alone. Mechanical thickening. Mechanical thickening techniques involve the use of mechanical equipment such as rotary drum thickeners, gravity belt thickeners or centrifuge to increase the solid concentration in sludge. Rotary drum thickeners utilize rotating drums with internal flights to dewater and compress sludge, while gravity belt thickeners use gravity and filtration to remove water from sludge. Centrifuges accelerate the sedimentation process by spinning sludge at high speed, separating solid from liquid by centrifugal force. Belt filter press. Belt filter press dewater sludge by passing it between two porous belts under pressure. As the sludge passes through the belt, water is squeezed out and solids accumulate to form a thickened sludge cake. Belt filter presses are effective for dewatering and thickening sludges with high water content and are often used as a final dewatering step before disposal. Gravity belt thickener GBT. GBT utilizes a continuous belt filter to thicken sludge by gravity drainage and mechanical pressure. Sludge is fed into a porous belt where gravity drainage and belt tensioning helps to remove water and increase solid concentration. GBT is suitable for thickening both primary and secondary sludges and can achieve high thickening efficiency with low energy consumption. Rotary drum thickener RDT. RDT operates similarly to rotary drum screen, but with added pressure to squeeze out water from the sludge. Sludge is fed into the rotating drum, where internal flights convey it through the thickening zone, resulting in increased solid concentration. The RDT is effective for thickening sludges with high organic content and has a compact footprint suitable for small treatment plants. Each of these sludge thickening techniques have its own advantages and limitations, and the selection of the most appropriate method depends on factors such as sludge characteristic, treatment plant size, space availability, and operational requirements. Integrating efficient sludge thickening techniques into the wastewater treatment process can help reduce the volume of sludge produced, optimize treatment efficiency, and minimize disposal cost. So, by somehow this water has to be removed from the sludge before it can be disposed, and different types of techniques have been developed, whether it is rotatory drum thickener or belt press thickener and so on and so forth. Efficient sludge management in textile effluent. Effective sludge management is essential for ensuring the overall sustainability and environmental compliance of the textile effluent treatment processes. By employing appropriate thickening, dewatering, and disposal method, textile manufacturers can minimize the environmental impact of sludge generation while optimizing treatment efficiency and resource recovery. Efficient sludge management in textile effluent treatment involves strategies to minimize sludge generation, optimize treatment processes, and maximize resource recovery. So, for a good sludge management, it should have strategies which will first of all make less sludge generation. Otherwise, it will optimize treatment processes in such a manner that it will create less sludge, and so much so that this sludge that is generated, can it be reused or recycled for resource recovery. If that is how the sludge can be managed, then it is one of the best methods to do so. Some key principles for efficient sludge management. Minimal sludge generation. As I told you that at the very onset, if there is less sludge, there is less problem of sludge management. So, to optimize treatment processes, fine tuning physicochemical and biological treatment processes to maximize pollutant removal efficiency and minimize sludge production. So, somehow if a strategy is chosen such that it can yield less sludge, that is the best method. Source control. Implement measures to reduce the input of pollutants and solids into the wastewater stream, such as process optimization, water recycling, and pollution prevention practices. So, at source only we are making control that less pollutant water is generated. Selective chemical usage. Use of coagulants and flocculants selectively in an appropriate dosage to minimize excess chemical consumption and sludge generation. Thickening and dewatering. Optimize thickening efficiency. Implement efficient thickening processes such as gravity settling, dissolved air flotation or mechanical thickening to increase solid concentrations in the sludge. Maximize dewater performance. Utilize effective dewatering technologies such as centrifugation, belt filter presses or vacuum filtration to remove water from the thickened sludge and reduce its volume for disposal. Energy recovery. Consider opportunities for energy recovery from the dewatering processes such as utilizing biogas generated from the anaerobic digestion of sludge or capturing heat for on-site use. Resource recovery. Biogas production. Explore anaerobic digestion as a means of stabilizing organic matter in sludge while producing biogas for energy recovery. Biogas can be used for heating, electricity generation or as a renewable fuel resource. Biosolid utilization. Treat stabilized sludge, that is biosolids, to meet regulatory requirement for beneficial reuse as soil amendments or soil fertilizer in agriculture, land reclamation or landscaping applications. Nutrient recovery. Extract valuable nutrients such as phosphorus and nitrogen from sludge for reuse in agricultural or industrial application, reducing the need for synthetic fertilizers and minimizing nutrient pollution in water bodies. Compliance and sustainability. Regulatory compliance ensures sludge management practices comply with local regulations and guidelines governing solid waste management, wastewater treatment and environmental protection. Environmental impact assessment. Now, this is a very important topic which needs to be discussed in great detail. Environmental impact assessment. Conduct life cycle assessment, that is LCA, or environmental impact assessment EIAs, to evaluate the environmental footprint of sludge management practices and identify opportunities for improvement. Because only when we see the life cycle assessment of any chemical, and sludge is a combination of chemical, we will know what will be its long-term environmental impact and what would be the environmental footprint. Continuous improvement. Implement a system of ongoing monitoring, performance, evaluation and process optimization to identify inefficiencies and implement measures for continuous improvement in sludge management practices. Modern trends in sludge management. Modern trends in sludge management focus on sustainability, resource recovery and minimizing environmental impact. This is the bottom line. That means the modern trend is how sludge should be managed, that it is sustainable, it has a resource recovery and it has minimal environmental impact. And here are some key trends. Resource recovery. There is an increasing emphasis on recovering resource from sludge rather than simply disposing it off. This includes the recovery of energy, nutrients and other valuable materials. Technologies such as anaerobic digestion, thermal hydrolysis and gasification are being employed to extract energy from sludge in the form of biogas or biofuels. So, The modern trend tells that somehow if we can use this sludge for some kind of resource recovery, that is the best option. And so, technologies such as anaerobic digestion, thermal hydrolysis and gasification can convert this sludge into biogas or biofuel, which can be burnt and energy can be recovered from that. Circular economy approach. Now the time has come in the modern times that there is a lot of emphasis on circular economy. Sludge management is increasingly being integrated into circular economy framework, where waste materials are viewed as resources that can be reused, recycled or recovered. This involves exploring opportunities for beneficial reuse of sludge derived products such as biosolids in agriculture, composting and land reclamation. So, you see that now even sludge is looked up as a product from which very useful things can be extracted, and if that is so, then it can be run into a circular economy and it can become a resource rather than a waste or a dump. So, biosolid for agriculture or composting or landscaping for land reclamations can be also used, the sludge can be used in those manner as well. Advanced treatment technologies. Advances in treatment technologies are enabling more effective and sustainable management to sludge treatment. These include technologies such as advanced anaerobic digestion processes, thermal hydrolysis and chemical conditioning techniques that improve dewaterability and reduce pathogen and contaminants in sludge. So, by making use of advanced treatment technologies, the pathogens are reduced, the contaminants are reduced, and therefore, this is easily dewatered and the sludge can now be used for useful purposes. Decentralized treatment. Decentralized treatment approach such as small scale anaerobic digestion system or mobile dewatering units are gaining popularity, particularly in remote or unserved area. Decentralized systems can reduce the need for long distance transportation of sludge and provide localized solution for waste management. So, when we say that there can be some small units around the mill and there the sludge management can be done, then it helps to reduce the cost of long distance transportation of the sludge. Digitalization and automation. Digital technology and automation are being increasingly utilized to optimize sludge management processes, improve operational efficiency and enhance monitoring and control. This includes the use of sensors, data analytics and remote monitoring system to optimize treatment processes, reduce energy consumption and minimize environmental impact. So, in today's time when it is all digitalized and automated, these processes of sludge management also can be optimized, and by improved operational efficiency, the monitoring and control can be done very effectively, and therefore, the net result will be that it will have minimal environmental impact. Climatic resilience. Climate change adaptation and resilience consideration are becoming increasingly important in sludge management planning. This includes strategies to mitigate greenhouse gas emission from sludge treatment processes such as optimizing anaerobic digestion for biogas production and reducing energy consumption through energy efficient technologies. So, even to mitigate the climate change, which is somehow related to sludge management planning, this includes strategies to mitigate greenhouse emission from sludge treatment processes, and which will then be affecting by optimizing the anaerobic digestion of biogas for biogas production. So, regulatory drivers, stringent environmental regulations and policies are driving innovation and investment in sustainable sludge management practices. Regulations governing sludge disposal, reuse and treatment standards are increasingly focused on protecting environmental quality, promoting resource recovery and minimizing adverse impact on human health and ecosystem. So, because there are stringent environmental regulation and policy, it is mainly directed to prevent the adverse effect or impact on human health and ecosystem. If the sludge is just littered here and there, it is going to have an impact on the local communities, and therefore, everything has to be done in a very strategic manner. Public engagement and stakeholders collaboration. Nothing can happen in the modern time where sludge management has to be done in a more efficient manner. There is a growing recognition of the importance of engaging with stakeholders, including local communities, policy makers and industry stakeholders in the development and implementation of sludge management strategies. Public awareness campaigns, community outreach initiatives and participatory decision making processes can help build trust, address concerns and foster support for sustainable sludge management practices. Now, you will understand that sludge management is a very serious matter, and through this lecture I have tried to convey that sludge cannot be just taken as a dump which needs to be disposed somehow and somewhere. It has to be strategically seen whether any recovery can be done, whether this disposal requires, this sludge disposal requires incineration or landfilling, or whether it can be used as a soil fertilizer or so. By embracing these modern trends, wastewater treatment facilities and municipalities can enhance the sustainability, efficiency and resilience of their sludge management practices while minimizing environmental impact and maximizing resource recovery. So, the bottom line is that sludge management practices should be such that they should be minimizing environmental impact and maximizing resource recovery. So, in conclusion, we can say that by adopting a holistic approach to sludge management that integrates pollution prevention, efficient treatment processes, resource recovery and regulatory compliance, textile manufacturers can minimize environmental impact reduce operational cost and enhance overall sustainability in wastewater treatment operations, and particularly in handling the sludge disposal. Efficient sludge management in textile effluent treatment involves strategies to minimize sludge generation, optimize treatment processes, and maximize resource recovery. So, the crux of this chapter or this lecture is that such should be the sludge management system, which is so efficient that after the textile effluent treatment, whatever sludge is generated, it is minimum in quantity and has been produced by optimized treatment processes, so that the generation of sludge itself is very small in quantity, and whatever quantity has been obtained is devoid of pathogens and hazardous contaminants, so that it can be used for resource recovery. Overall, sludge generation is an inherent aspect of textile effluent treatment, and efficient management of sludge is essential to ensure the environmental sustainability and regulatory compliance of the wastewater treatment operation. So, we have to identify that sludge will be formed during the treatment of the textile effluent. It is for us to choose the best method for the treatment, so that minimum sludge is formed, and the sludge that is formed is out of such technologies that it has minimum or no contaminants, pathogens and hazardous chemicals, so that it can be utilized for resource recovery, like if it can be put in anaerobic digester, biogas can be produced, or nutrient recovery could happen, so that nitrogen and phosphorus could be evaluated and extracted. So, resource recovery is now more focused for sludge management. So, if we look at the whole process, that textile effluents have to be treated for removal of color, pH, temperature, turbidity, COD, BOD, TSS. When all that is to be done, some processes will generate sludge at different stages. Now, can we recover something reusable from that sludge? If we can do that, then we are actually recovering from the resource, and the size of the sludge is also becoming less. So, therefore, less effort will have to be made for its disposal, whether we are doing landfill, whether we are doing incineration, whether we are trying to use it for land reclamation, or we are trying to get nutrient or biogas or energy from that sludge. So, it is for us to decide, and the modern trends now emphasize that overall that is what is to be kept in mind: minimum sludge generation, optimize treatments processes, and maximize resource recovery. With this, we have come to an end of this lecture. Thank you.